This is math 2. We're going to do 118 to 124, and I'm pretty sure that we're going to have to probably stop somewhere halfway in the middle and then do another video. 118, we're going to graph f of x, figure out what the y-intercepts are and the x-intercepts are. And I hate to say this, but I am really exhausted, so we're going to do this the fast way on 118. We're going to plug it into the calculator, and we're going to use Desmos because Desmos is a friend of ours. So x squared plus x minus 6. So right away you should be familiar enough with the standard form that you can tell me that at 0, -6, that's where it intersects the y-axis. The question is where are the intercepts for the x-axis, and that's what we're going to use the computer graphics to actually find for us. So the graph looks like this. Okay, we have 2 and -3 is where you have your x-intercepts. So at -3 and +2. And then if you were to find the vertex of this, then you go right in the middle between those two. So let's see, right in the middle would be, okay, that's 2, that's 2. So I've gone a distance of 2, I've gone a distance of 2, so then halfway in the middle is going to be at -0.5. So if we take -0.5 and we plug it in to the equation, we have, let's see, -0.5 squared plus -0.5 minus 6. And if you work that out, you should get y equals, let's see, 0.25 minus 0.5 minus 6. So you should get y equals negative something or another, -6.25? Yeah, -6.25. Okay, so your x-intercept for your vertex, I should say, because it really didn't ask for it, but you have to graph it. So if you have to graph it, you might as well graph it correctly. So your x-intercept should be at -0.5, which is halfway in between your two x-intercepts. Sorry, your vertex is halfway in. The x-coordinate of your vertex halfway between your x-intercepts, and then you plug -0.5 into the equation, and you get your vertex at 0.5 and -6.25. Okay, so there's your vertex. Okay, and then it says if c of x equals 6, what is g of x equals f of x plus c of x? So we're really just combining functions here. So if f of x is x squared plus x minus 6, c of x is 6, so I'm going to add 6. I'm going to add 6 because c of x is 6 right here. So your final result is that g of x is equal to x squared plus x. Because -6 plus +6 goes away. You have 0 pair there. So you have g of x equals x squared plus x. Now you have to actually graph this one also. So if you want to do it the long way, by all means do it the long way. You can factor, you can complete the square, you can do a quadratic, whatever you prefer. I'm going to do it on the Desmos again because it's just going to take too long and I have to get through other stuff. So if you actually graph it, this one, g of x, it will look like this. This is the same graph as I have the other one in. So you have -1 for the x-intercept. You have 0 for the other x-intercept. So if you graphed it the long way, those are the two values you should get for x. And then halfway in the middle is going to be -0.5 again. And then if you plug -0.5 into the equation, you should get 0.25. Okay, so you should get -0.5, comma -0.25 if you plugged it back in. So your vertex is there. Now, it did say determine the x-intercepts and the y-intercepts of g of x, then compare the graph of f of x and g of x. So it actually doesn't have I lied. It does have a y-intercept, but it's really at 0 because it's just plus 0 because that kind of went away. So your x-intercept at 0 is also your y-intercept at 0. So this is the function, all right? And it came from this one. So what you should notice is that they both have the same x-coordinate for the vertex. The only difference is that you took this one at negative 6.25 and you shifted it up 6 units, technically, at negative 0.25. And that should make perfect sense since the reality is you shifted it 6 units by adding plus 6 when you add the constant function to it. All right, that was 118. 119. The interesting stuff. Write a set of equations for the piecewise defined function shown at the graph at the right. Be sure to include domain for each function. So the first thing that I asked people to do was actually to, if you were to just graph both lines, what would the equation of both lines be? So you have this equation here, or this line over here, I should say. And then you have the second line over here. And what would the equations of those two lines be? Well, for the one in, I'm going to call it the one in red. Okay, if I were to extend this out and actually write an equation, it would be y equals, let's see, it hits at 1, so it would definitely be plus 1. And the slope would be up 1 over 1, up 1 over 1, up 1 over 1. Okay, so it'd be 1 over 1 x plus 1, or better known as just y equals x plus 1. Same thing, right? Guess you don't really need that. And then the second one, which would be this one down here, the green one, it would be y equals, let's see, hits it at negative 3, so it's going to be minus 3. And then we're going 1, 2, 1, 1, 2, 1, 1, 2. Okay, so it'd be up 2 over 1 x. Okay, they're both positive, so they're both going to have positive slopes. Or better known as y equals 2x minus 3. I guess you don't really need that. Okay, so those would be the two lines. Now the question is, where's your cutoff point? What's your boundary point? And hopefully you actually notice where the boundary is, where there's a gap right there. Since your boundary line is going to go through this way. Okay, the boundary is somewhere around 2 for the x-axis. So now we're going to write our function, our piecewise function. So it's going to be f of x, because I don't think we have anything else to work with. Okay, so it's f of x equals, well, I'm going to put the boundaries first. Actually, no, I lied. I'm going to put the equations first. So we have y equals x plus 1, the green one, and we have y equals, oh my goodness, I can't believe I did just y equals 2x minus 3. Sorry, you don't need the y's because you already had f of x. Okay, so it's x plus 1. And then 2x minus 3. All right, so x plus 1. X plus 1, which is the red one, is going to be true because that's, the part that is in pencil, you don't really need. It's going to be true for the red one whenever x is going to be on this side. So the right side of positive 2. The right side of positive 2 are all bigger numbers than 2. So everything, x, technically, that is going to be greater than 2, that's when the red one takes place. So it's closed circle on the red one, so it's going to be greater than or equal to 2. And the same thing, well, the other version of it for the green one. Everything on the left side of the 2, all the numbers over here on the x-axis on the left side of the 2 are smaller than 2. So, and it's an open circle where the green one is, so I'm not going to put anything underneath it. So this is your final answer for the piecewise function for those two graphs. Or, yeah, that was 119. Okay, 120. This should be pretty simple. I'm just going to straight up work it through. So he has placed some red, 3 of the reds, right? So 3 of the red ones, 7 of the blue ones, 7 blues, and then 2 of the yellows. So I guess we could use yellow, 2 of the yellow beads, 2. All right. 3 plus 7 is 10, plus 2 is 12. So all of them have a probability based upon the total, which in this case is 12 of the beads. And then the expected outcome is you multiply the money, how much you're expected to win, by the probability of that outcome. So in case of 3 out of the 12, you're going to win $3 if you get a red hat. You're going to win, actually you're going to lose $1 if you get the blue hat, and then you're going to win $10 if you get the yellow hat. I'm sorry, the yellow beads. I'm really tired, guys. In the hat, sorry. So you multiply that out, you get, you should get somewhere close to 11 out of 10, or better known as 1.83. So technically, to just make sense of this problem, the person, or actually Mr. Kai, is going to win $1.83 on the average playing this game. So the question is this game fair? No, it's not fair. If it was fair, it should have an outcome expected value of 0 because nobody wins and nobody loses. That's fair, right? But since you're actually come out ahead by $1.83 every time you play the game, then you're actually going to win. So the player will come out ahead over time. So students may want to play the game. All right. So if you get a 0 on your expected value, that's when it's a fair game. All right, 121. Chad is entering a rocket competition. Chad programs his rocket to launch straight up into the air with the function h negative 16t squared plus 92t, where h represents the height in feet, t represents the time in section. How long after the launch does it take the rocket to reach the ground? So basically what you want to do is, I don't know, set up a little bit of a table. So launches from the ground. It goes into the air and comes back down again. So the question is, when does it come back down? As in time in seconds. All right, so what is the value of x? Or in this case, what's the other x-intercept? You know, one of them is at 0, 0. But what's the other one? And the fastest way to do this, since negative 16t squared plus 92t plus, well, we don't have a plus anything, so technically it's plus 0. So what I want you to do is, this is not going to be a very nice function, so just use your quadratic, plug it in, and get the values of x. One of them should be 0, and you should get another one, and it should be a distance away, because obviously it's going to take a few seconds. Okay, and then write and solve an inequality that shows at what times the rocket is at least 76 feet high. Okay, that's a little different. I'm going to need another piece of paper for this. Okay, this works. So when you find the value of x, plug it in there. That'll give you your time when it lands. Okay, part B is a little weird. So write and solve an inequality that shows when and what times the rocket is at least 76 feet high. So you want to know the height, right? So the height at height is equal to negative 16 times squared plus 92 multiplied by the time. So the height is going to be 76 feet high, at least 76 feet high. So you want it to be over 76 feet. So 76 feet is the least that you want it, the smallest that you want it to be. You don't want it to be equal to it either. You want it to be more than 76 feet high. All right. And the best way to do this is to solve the inequality. So in this case, the way that you would solve it is to Well, just pretend it's equal to. All right, and then subtract 76 from both sides. So you get 0 equals 16t squared plus 92t minus 76, and solve it for the time, or in this case, you can say the x if you want to. Use a quadratic again if you're stuck. Your A is going to be negative 16, your B is going to be 92, your C is going to be negative 72. Plug it all in, and then find out at what time intervals, right? Because that's what you're really solving. At what time intervals does the rocket actually is in the air above 72 feet? Okay, and you should get, so find those out, right? Do the quadratic, work it out, and then in order to qualify, the rocket must be at least 76 feet off the ground for 4 seconds. Does Chad's rocket qualify? And what is the appropriate domain for the function in this situation? So hopefully you understand how to do that, because you're going to get an inequality on the test. I guarantee it. So please make sure you finish the rest of it and get the times. And to finish it off, here is the rocket function on Desmos. So I can tell you right now that it's going to be at 76 feet. So 2, 4, 6, no, 75. So this is 75. So at 75, there's 75. So between 75 and that's 77. So this is 1 second. So between 1 second, somewhere around between 1 second and, no, it's probably 1 second. So between 1 second and, that's 5, 4. Oh, well, it's at least. So this is 1 second. From here to here, it's 1 second. From here, it's 2 seconds, 3 seconds. Oh, it doesn't qualify. Okay, well, 1 second, 2 seconds, 3 seconds, and then 3 and something. So it's not in the air long enough. Sad to say, Chad does not qualify. As far as I can see, he doesn't qualify. He's only above 76 feet for 3 and something seconds, so less than 4 seconds in the air. All right. And then what's the next one? What happened to the next one? So what is the appropriate domain for the function in this situation? Well, I don't know. I guess we're landing somewhere less than 5. So you go from 0 to, I don't know, from 0 to 6. That should be okay. So you definitely have to start at 0, because being in the ground or past 0 doesn't make any sense. So your domain, the time, should probably be somewhere between 0 less than or equal to, less than or equal to, whenever you land. So whatever value you found when you actually did the landing point, wherever it landed, that's going to be your domain. It's going to go from 0 to the time that you land. All right, that was 121, and I think I'm going to stop this video right here.